Hi y'all, welcome back to another round of vectors, and I apologize for the extra space today on your screen. I'm trying something else out differently. I wasn't happy with some of the resolution of the previous two videos, and after some reading found out that maybe it's because I'm cropping my screen when I'm doing the recording. So today we're dealing with the full screen, and if it becomes too troublesome or if I don't notice the difference in quality, then I'll go back to a smaller viewing area just so that everything ends up being larger. So today what we're looking at here is we're dealing with vectors. Now, if you recall from the last video, we dealt with how to represent them geometrically with an arrow and then an arrowhead. So the length of the arrow representing the magnitude and the direction being indicated by the arrowhead. Algebraically, we represent them as a triplet of numbers, or if you prefer, in hat notation. So if that's, hopefully that all rings a bell from your reading from watching the previous video. If not, go back and take a look at that. We're not going to go over that again. Today's video is going to be dealing with three main topics. We're going to be talking about addition of vectors. So how do we add these things together? And after we establish that idea, both graphically and algebraically, then we'll move on to what the negative sign means. So we'll put negative signs. What does that mean about a vector? And lastly, we'll go into multiplication. And here we're only going to deal with one type of multiplication. There's actually three types that you can do with vectors. I'll save the other two for the next video. So right now we're just going to be sitting here doing these three things. So let's start off graphically. So let us get a couple of vectors. We'll do vector A, something like this. We'll do vector B, something like that, just to give us something to start with. We put our arrowheads on, and I'll call this vector B. We'll call this vector A. Okay. So just some generic run-of-the-mill vectors that I've put together. There's nothing special about these. These are for illustrative purposes. And the idea, or at least the question is, what do I get if I take vector A and I add it to vector B? And one of the first things I should point out is when you add two vectors together, you end up with a vector. So this will be some generic vector R, and I'm using capital R because generally we talk about the resultant vector. I take these two vectors, A and B, I do some calculation, what's the resultant vector? So I'll call that as a capital R, but this is usually called the resultant vector. Now the question is, how can we actually get this geometrically? And what we're going to do is we are going to use our handy-dandy idea, about moving vectors. So vector translation. So let me go ahead and let me do a little bit better. I think I do better there. Let's go ahead and select vector B. And what we are going to do is translate vector B. And we're going to translate in such a way. Remember, I can move this around any way I want. As long as I don't rotate it, it's still the same vector. So moving it around on the screen is fine. And what I'm going to do is I'm going to take the tail, or excuse me, yes, the tail, the part that does not have the arrowhead. I'm going to take the tail of vector B and I'm going to place it at the tip of vector A, like so. Leave it like that. Looks good enough. And so now I've got the tail of vector B on the tip of vector A. And of course, this method is generally referred to as the tip to tail method. That's kind of the tip to tail method. So I've placed the tail of vector B on the tip of vector A. Now simply the resultant, and why don't we go for some different color here. The resultant is the vector that stretches from the tail of A to the tip of B. So right here, this is my vector. There is my resultant, and I should also make sure to include an arrowhead. There is my vector R. And we're done. Pretty simple, right? Now you could say, wait a minute, Greg, I don't like that. What happens if instead of a plus b, what happens if I do something like b plus a? What do I get then? I say, excellent question, I'm glad you asked. Let's go ahead and we'll take this. Let's take a copy of it. If I can figure out how to do that, paste. We're going to move that copy downwards. There we go. So we've got a copy of that now. And of course, I'm not interested in vector r. We say, oh, of course, this is a plus b. I want b plus a. So let me go ahead and get rid of that vector r for the time being. There it goes. Gone, 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 gone. And let me just patch up that little piece of a here. Okay. So you say, well, wait a minute, Greg, I don't like that. I don't like vector A and vector B. Let's do the tip to tail method again, except this time we're going to use vector A. And we are going to move vector A. We'll go ahead and move it over. Oops, excuse me, I ran out of space there. We'll move it over right here. And we're done. Oh. Well, now I've buggered it all. There we go. Excuse me. It takes a little bit of getting used to. Now I've got vector A. So now you would say, okay, well, I've done b plus a here. Let's go ahead and draw in the resultant vector. Again, it goes from the tail of b to the tip of a. And excuse the labels are in the way now. And we'll put an arrowhead on it. And there's something you should notice now. If I compare my vector r for the first case, where I did a plus b, and I do it for b plus a, I compare those two resultant vectors, you should hopefully notice that vector A plus vector B is the same as vector B plus vector A. In other words, the order does not matter. These two vectors are, I believe it's called commutative. Vector addition is commutative. It doesn't matter if you do A plus B or B plus A, you end up with the same answer. Cool. That's all there is to graphically adding vectors. You slide the tail of one to the tip of the other, and then you draw the resultant vector from the two, I'll say, unoccupied ends of the vector. Pretty simple. So let's go to the algebraic way. Okay, so leading on, we've done the geometric vector addition. Let's go for the algebraic method. So I'll start with some generic vector. And here I'll use A, and we'll use I'll call this AX, call this AY, comma, AZ. In other words, I've got my vector triplet, and I've got a variable representing the X direction, the Y direction, the Z direction. And we'll do the same thing for vector B. So this is, of course, assuming we've put down our coordinate system. We've counted out the grid lines. We've done everything that we need to do in order to get those three numbers. So now we have our algebraic representation of those two vectors. And how we do vector addition algebraically is we add them. Well, of course we add them, but how do we add them? We add them component by component. So the resultant vector, in this case, will be vector A plus bx. In other words, the x component added together, the y component added together, and the z component added together, az plus bz. And we're done. Alternatively, if you don't like writing it this way, you could write it as, for example, you could write it as a summation. That's a little bit more goofy, but we could write it as something like the sum of AI plus BI. Something like that. And then there's some fancy hat notation. We'll call it E hat I. So if you happen to run across this, this is a different way of actually writing that summation. It's hat notation, but it's a little bit more compact, and you might see this in your future careers. So let's get some idea about why that actually works. So let's again draw in our coordinate axes. Better do that, and I'll make my x-axis extra long. So we've got that. We'll put our y and our x in here, x, and I guess we better just tick mark this out. Okay, and let's draw in our vectors again. Let me do it a different color just so that we can actually see them now. So we'll do them as this lovely green. Why don't we do that? So for sake of argument, I'll do, there's my A vector, and here's my B vector. Okay. We've already established that it doesn't matter if I do A plus B or B plus A. So we'll leave it like that. Say, oh, Greg, you cheated. You made it exactly the right length. Well, of course I did. There we go. Okay, and we have our vector r here. So stretch that vector r, the resultant, all the way up. Boom. And we'll put an arrowhead on it. Great, and there's my vector r. Okay. So now let's take a look at this for a second. Why does this actually work? Well, vector A, you notice, in the x direction, it's 1, 2, 3, 4, 5, 6, 7, 8. We have it 8 in the x direction. And then we notice that vector B extends an additional 1, 2, 3, 4, 5, 6, 7. So this is 15. So you notice that, okay, the first 8 comes from vector A, and then an additional 15 in the x direction, or excuse me, an additional 7 in the x direction comes from vector B. So vector r stretches a full 15 in that x direction. That's what we see here is A plus the x direction, it's A and B. Now in the y direction, A contributes nothing, right? It's perfectly along the x-axis, so 0, whereas B contributes, I don't know, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. So now I lost track of where I started, 9. Starts in the 9 direction. So again, the y component of B contributes to the overall component of the resultant. So that's just kind of giving you some intuition about how this thing works. The deeper idea, though, is that I'll point it out here. Our x direction, our y direction, and our z direction are all independent. In other words, moving in the x direction does not contribute anything to the y direction, or moving in the y direction doesn't contribute anything in the x direction. A different way, the reason for this, the deep mathematical reason, is that we say they are orthogonal. Orthogonal. And it turns out it's really nice to write vectors when you have orthogonal coordinates. Coordinates x, y, z, or if once you get into multivariable calculus, you'll see a different coordinate system, r, theta, and phi. This is also a very convenient one. You use this, for example, in latitudes and longitudes. Or you'll see, this is called spherical, by the way, spherical. Or you'll see something like r, theta, and z, which is known as cylindrical. Now, of course, we're not going to deal with that right now. That's a little byline for the math people in the room, including myself. So the reason that this works is really that x, y, and z are orthogonal. In other words, they're perpendicular. So motion in one direction does not affect anything going on in the other two directions. I emphasize it now because this will become very important when we start dealing with 2D motion. This is what allows us to break motion in the x direction apart from motion in the y direction. Okay? So stay tuned. And that's it. This is the algebraic representation, or this is how we actually do addition, is that we add by components. So the next question, or at least the next subject up for debate here, or discussion, not debate, I'll tell you, I mean, yeah, it's not debatable. The next idea that's up for discussion is, what about negative signs? What do negative signs do? So let's get rid of that. Negative signs, question mark. And as long as you're comfortable with this idea of vector addition, you already know what a negative sign will do. Let me go ahead and write it out here. So we'll start with, I don't know, I guess it doesn't matter, but we'll start off with the algebraic idea. So if I have some generic vector A and I subtract vector A, what do you anticipate getting? I mean, just like a regular number, vector A minus vector A, or we could alternatively write this as vector A plus, I'll put negative vector A. That's also an idea, but I think all of you came up with the idea that you should end up with nothing, 0. This tells us what a negative sign is doing. If we have a vector A and I put a negative sign in front of it, well, let's see here. Vector A would be pointing this way, for example. Just, again, some generic run-of-the-mill vector. If I call this vector A, if I add a negative A, I have to end up at the exact same spot that I started with. So in other words, if this is vector A, negative A, let's go ahead and take that, we'll copy it and paste it, move it around, negative A, and let's see if we can do this. Ah ha ha ha, must be pointing in exactly the opposite direction. In other words, here is negative A. So that when you add the two together, A plus negative A, you end up with 0. So a negative sign simply flips the vector by 180. So we'll put negative sign, flips vector by, I'll put 180 degrees, or by pi. If you have a vector, the negative of that vector points in exactly the opposite direction. Boom, you're done. That's all that negative signs do. Cool. Let's now try something else. So we've got negative signs, we've got vector addition. Let's go ahead and do the last one, multiplication. Multiplication. And I have to, as I've warned you, I said there's 3 different types of multiplications. Let's do what's called scalar multiplication. In other words, I take a number and I multiply it by the vector. What happens? And here's the trick, and I want you to remember this because it's been 20, 30, 35 years for me. Well, not 35, I guess, but at least 30 years, okay? And here's the trick, okay? Don't forget, multiplication is simply repeated addition. I'll say that again. And I know, remember, it's hard to remember when you learn multiplication, but multiplication is repeated addition. And you know how to do addition. You know how to add 2 vectors. We just did that. So again, let's say I want to add 2 vectors, but this time I'll say it's vector A. Say it's vector A, here we go. And I want to add to it a second vector, also named A. So let's move vector A. So I'll do the tip to tail method here. I'll put the 2 vectors together. We've got A, and you know that this would give you a vector length of, the resultant vector would have a length of 2A. In other words, if I drew this resultant vector out, I've got a tip to tail method. The resultant vector would be one that stretches that entire distance. There we go. Okay. In other words, if I multiply by a scalar some number, what ends up happening is that stretches my vector. Since I multiply by a scalar greater than 1, that stretched my vector A, so that my resultant vector was some multiple, some stretched length of the original vector. Similarly, if I go ahead and I multiply by, say, 0.5, what happens if I have something like 0.5a? What will that look like? Well, you know how to get 0.5a. 0.5a is simply a, I'm going to rewrite this, minus 0.5a. Okay. And you know, okay, well, I guess, yeah, come to think of it, well, I mean, you could write it as a subtraction. So a minus 0.5a, Okay, well, you know the negative sign flips the direction of the vector. You know you have your original vector, so let's go ahead and put this down. We'll put paste. So here's A, and then I'll put copy and paste. Let me rotate it. I'll rotate it 180 degrees. If I can get exactly on 180. There we go. I've rotated it, and let me scale it while I'm at it. I will scale it down 50%. There we go. Let's move this back out of the way. So I'm sorry, it's a bit thin, but now you see what it is. I've got my vector A, I've got 50%, right? It's 50% smaller and a negative sign, so now it's rotated. And so my final vector R, my resultant, goes from the tail, unoccupied tail, to the unoccupied tip. And I'll say, of course, I've drawn these slightly offset so that we can actually see everything. This would truly be on top of each other. So I've got something like that. There's my vector R, resultant. It's half, if I actually marked it out, it is exactly half the length of A. So, being said, scalar multiplication, if the scalar is greater than 1, stretches or increases the length. Stretches. And please note, it stretches, but it keeps the same direction. R is parallel to A. The resultant is parallel, or at least maybe I should say, I'll say a little more generously, along the same line defined by vector A. If the scalar is less than 1, it shrinks it. And that would be in this case. You see that it's shrunken. It's shorter than A. And that's it. So I would say please go back and review, but the idea of vector addition, that's kind of the key concept here. If you understand how to add vectors, then we can rationalize or logic our way through how to subtract two vectors, and also going through vector multiplication by a scalar. Of course, you could say, what about division by a scalar? Well, keep in mind, division by a scalar will still result in some number either greater than 1 or less than 1. So you'll still get that stretching or that shrinking effect. Thank you for your attention. I'll see you next time.